So hi everyone, and welcome to the second after show of the AI Hardware Show 2023. Joining me, Sally from EE Times. Good to have you. And if you've just come from our second episode, welcome. If not, well, the link's in the description, but we'll take you through some of it anyway. This episode is been a bit of a mix.
More of a mix than the last episode, yeah.
So, I mean, we haven't addressed it specifically yet, I guess, but the whole thing of between training and inference, companies tend to either do one or the other. So we've kind of done a mix here. Oh, I guess
it's like either you're a training company or you're not, I guess.
Yes.
You do training and inference or you only do inference.
Yeah, just because training has that higher barrier to entry. And stuff.
It's a completely different workload, yeah.
Yeah. So this episode of the AI Hardware Show is sponsored by Tenstorrent. That's Tenstorrent, the Jim Keller company. Find out more later in the episode. First chip we spoke about this episode was from Axelera.
Yeah, very cool. Young company, European company. So Axelera, as you heard in the episode, they've been incubated within Bitfury, which is a crypto company.
Yeah, blockchain, crypto.
Yeah. So
this is AI. What are you doing bringing crypto in?
So they incubated an AI accelerator company within the company. They have a chip division.
Yep.
For making their own accelerators for the blockchain and all that good stuff. They incubated Axelera.
Right.
They've spun it out now. Axelera has licensed some stuff from IMEC as well. And they got some people from IMEC, and they're doing a digital in-memory compute design, which is going to be quite good fun. The figures that they've shown so far, quite compelling, 33 tops per watt, which is pretty much state of the art at the edge.
That sounds market leading.
That sounds market leading. We haven't seen the chip yet, of course, so it's still to come. They're still relatively early stage.
So that's theoretical peak tops, not real world.
I think so. Yeah,
tops,
we haven't measured the actual power yet of how much it takes.
Yeah.
So it's still to come, but sounds very promising. One thing he said is the eventual chip will be more like hundreds of tops. So robotics, drones,
right,
that kind of thing. Not ultra low power, even though the power efficiency is very, very good.
So something in about the 10 to 15 to 20 watt range, I guess.
I would think so for something. You'd think so for something like that. But
so you said IMEC, right? Can you explain to everybody what IMEC is?
So IMEC is one of these innovation institutes that basically does a bunch of R&D on semiconductor stuff at different levels, right? From process and device stuff to some of the higher levels as well. So yeah, it's like they will license their IP to you, come along with as a company and license some of their cool R&D that they've done and build a company around it. Sounds very cool.
But don't steal our engineers. Oh, wait.
Yeah, I'm not sure to what extent the engineers are stolen or whether they borrowed them or what happens exactly on that front. But some of the IMEC staff that have been working on this IP will transfer to Axelera.
So I have an open invitation to go see IMEC in Leuven.
You should do it.
I should do it.
I went there many, many years ago, and at the time, they were breaking ground on a new building, and I want to see that it eventually got built, right? It was probably 10 years ago. So
they now do a yearly event called IMEC Futures.
Right, yes.
So I missed it last year, but we should try and get
maybe next year.
Yes. Yeah. So IMEC, I've actually featured in a video recently where I spoke about process node technology down to the 0.2 nanometer,
this is cutting edge
36.
stuff, right?
It is. Every time I go to an IEEE conference, they're there with so many papers, whether it's about transistors or the upcoming IEDM conference. They're mostly talking about quantum computing.
Yep.
And then all the way up to AI IP with Axelera. So
absolutely. It's such a broad kind of, it's so many different interests, but all within deep tech semiconductor industry.
Well, there's IMEC, there's Fraunhofer, there's a few others. All seem to be European based.
Oh, ETH, Zurich. There are a few others. It's quite nice that we have these here in Europe, I think. Well, I wish we had some in the UK.
Well, Europe doesn't have much semiconductor manufacturing. So
we're just doing the R&D here in Europe, and then
ASML and good Belgian company, I guess.
Okay.
So, so going from what we do have in the UK is Graphcore.
That's right. Yes. Talk about British semiconductor company.
Yeah. Yeah. So Graphcore, if you're not familiar with them, they were one of the one of the first VC-funded companies to actually have AI silicon in the market.
Yeah.
Like 2016.
Yeah.
I remember seeing brightly colored PCIe cards in collaboration with Dell. The idea is that you buy 8 of their IPUs, did they call it? And I actually spoke to them at an event where they were showing this, or at least showing the generation after that product.
Yeah.
And I asked, why aren't the cards brightly colored anymore? And they said, because when customers were replacing a card, they didn't want one that had different colors on it.
Really?
Because they didn't know if it was the same thing.
Oh my goodness.
And they wanted to replace like for like.
Okay.
So they were trying to be innovative on the package, on literally the package.
Backfired.
Cooler, and it backfired.
Okay.
So that's why everything since has been consistent. But in the episode, I talk about Bow and the good computer. So this is their third generation IPU. And what Bow does compared to what the previous IPU did is they're being innovative on wafer level design on the packaging. So
they have the sandwich.
A sandwich, yeah. So what they've done is they're using TSMC's wafer-on-wafer technology, which means you get a wafer of chips and you get another wafer underneath. You line them up with the notch that's in the wafer, and then you do hybrid bonding together. And what Graphcore have put on the bottom of that is their deep trench capacitors, so they don't have to actually put them into the chip themselves, and some of the routing. This has provided them a 30% speed up.
Or 40%.
Or 40%. With no additional power consumption.
Yeah.
Well, I mean, it's still on the voltage frequency curve.
Yeah.
But it's nothing additional for the sake of having wafer-on-wafer technology, which is good because as we get to more advanced process nodes, higher frequency parts, you need things like deep trench capacitors, and they take up space.
You need to deliver power more efficiently, deliver it faster into the transistors, and it's a very good way of doing that. I think they've proven that it absolutely works. Yeah. They're TSMC's lead customer on this, so they're kind of the first customer to do this or to show this, which is terrific because it does work. I mean, the overall effect is let's just turn up the clock speed 40%.
Yeah.
So they haven't changed the architecture, they haven't changed anything else. It's like literally just this new packaging technology, and let's just crank it up, basically. And it worked.
I mean, added cost, obviously, doing more advanced packaging.
Although cost to the customer, similar or same?
They said
that's what they said.
They said it was the same cost. So
that's what they said.
Its gross margins would be lower. Or maybe TSMC is giving them a special price for being lead first.
We can only speculate.
For you,
we don't know.
Price. Yeah. So with deep trench capacitor, if you don't have to design it, also makes your power and signaling a lot easier. You're not having to deal with interference. And then the whole thing is Graphcore wants to put a bunch of these into a massive supercomputer that's doing petaops of compute for machine learning, which they're calling the Good Computer, named after Jack Good. I still want to make a video on who wants a good computer. That's the title. Though I will have to make it before Graphcore may end up in oblivion. This is so...
We don't know what's going to happen. I mean, to be fair to Graphcore, they've been around for a long time and they're ahead of the game with their product. They were one of the ones that were out first, and they are really aggressive, taking on NVIDIA and others. So we don't know what's going to happen yet, but reported layoffs at Graphcore.
Well, so actually, it's a good point you bring up NVIDIA. So in the last episode, we spoke about NVIDIA having 90% of the market, especially in the training.
Yeah.
So if you want to compete, it's very hard to go up against NVIDIA in that front unless you win. Nobody buys a chip better than NVIDIA if it's only 20 or 30%.
Absolutely. It's got to be 10x, basically.
Yeah.
So otherwise, there's no point rewriting all my software or changing over, right?
So, Graphcore have done ML perf data, which were the benchmarks they selected were favorable, though the comparisons were a bit oblique.
Yes, as it always is with benchmark data.
Yeah, and obviously that's not real world what customers are running either. As much as ML perf and ML commons want to get it representative, ultimately it's not. But so
it's like, it's not perfect, but please don't take it away.
Yeah.
We love having the benchmarks to compare things. Please don't take it away. But some improvements maybe.
So as I say, Graphcore, one of the first in the market, aggressive. 2016, I think their first chip came out.
So they kind of are ahead of the game, or were ahead of the game, but was that too early? Have we run out of money now? Again, we can only speculate on what's going on over at Graphcore, but they have a product in the market and it does work.
They've VC funded right now to about 700 million.
It's a lot.
Of which they say they've still got a good chunk left. But there are reports saying that revenue last year was only maybe 5 million for a burn rate of 200, which is, you need it to be the other way around. Right. So that with the layoffs, to your point, I think, were they too early? I mean, if it was any other industry because AI is just so fast moving, right? You build it, even the leading edge, even the companies that are making most of the revenue, they're coming out every year, new generation. As an AI startup, you can't have new product 3 years later, new product 3 years later, new product, because you don't generate enough revenue in the interim to stay afloat.
Exactly.
So, I wish them well. I do, because we do
I
like to see...
absolutely want to be behind a British semiconductor company, of course. I think they've got a compelling story. I think it's different to whatever is out there, but NVIDIA is a very tough competitor.
Yeah.
And everyone else feels that too, right?
Is it just could they pivot and market it to something else, or is...
No.
Like
what?
Well, I don't know. It's their next generation product, they've said, is on TSMC 3 nanometer. Whether it's going to have this wafer-on-wafer bonding yet, they haven't said. But I at this point, if their burn rate is what's being reported, if their revenue rate is what's being reported, are they still going to be around when it's ready?
And this is something that if I'm buying this to put this in my data center, that's something I have to consider carefully as well, right? If I move to Graphcore now, or to any other AI chip startup, if I move to startup hardware now, what do I do in 3 years when they potentially are not around anymore?
Roadmap?
Do they exactly? Do they have enough money to make it for another 3 years?
Yeah, or am I going to be left having to support this myself?
Effectively, yeah.
And then rip everything out and go with something
and
else.
Then change to some other kind of hardware when they're not around, and change all my software again.
Yeah. I don't know.
It's a tough sell.
It's right now, if we're talking about winners and losers in the AI space, if we ignore the companies that Intel have left in its wake, then we've got Mythic, who are no longer, which we're actually going to talk about next episode. And then, the other kind of company on the negative is Graphcore. So
I don't know if I'm that negative. I'm still right behind them. I really want them to succeed. But maybe it's a little tricky to know what's going on over there right now.
Well, when Nigel gives you a call, let me know.
Yeah. If you're watching this episode.
Yeah.
Uh-oh.
So next up is a company that I think is named absolutely stupidly. They call themselves GrAI Matter, but GrAI is spelled GrAI.
Yeah.
So that's GrAI Matter. Right.
It's grey matter, like in the brain, right? It's one of these brain-inspired
I get that bit.
type of things.
But it's we were talking about this earlier. In terms of companies that are named weirdly, ThinkEye, which is now Blaze.
They've changed it.
So
there are some worse ones around.
Do I know any of them? I mean, Light and Intelligence.
There's one that I really hate. It's escaped my mind right now, but no, there are way worse. Honestly, there's much worse.
Okay. Fair enough.
Maybe we can add that in after.
So, GrAI Matter. GrAI Matter
are very interesting company coming from the neuromorphic side, but not actually. It's an interesting thing. They basically take some concepts from neuromorphic computing, but then implement it in like digital hardware. Basically, I think it's an interesting thing. They basically are like, let's take some concepts from event-based sensing, which is let's take a camera and then let's look at only things that change in between the frames.
Spiking neural networks.
Not quite. It's like, let's look at what changes between the frames and then let's only do AI on that data. So it's very low bandwidth. It can be very low power. I could combine it then with spiking networks and try and get some synergy, but that's not what they're doing here.
Yeah.
They're just using relatively conventional hardware, let's say. But the point is, it's like, let's make the data really sparse and then let's operate on it. And then let's save loads of power and it can be really, really fast. And then let's output something which is still, let's reconstruct that back to full frames and make something which is really high quality then on the output as well. It's a slightly different play from most things where at the edge where it's like, I only want the metadata. I want to know, is there a cat in this picture or not? Yes or no. This is more like, let's do manipulation of the image for whatever reason.
Right. Okay.
So I need a high quality output as well. So it's like I extract data from it and then kind of
use it to change what it looks like to the...
Yeah, exactly. Yeah, let's do...
So like Snapchat filters?
That kind of thing, absolutely.
Right.
But it might be more like overlaying stuff or overlaying boxes around a car that's coming or something like that.
We've all seen the AI demos of self-driving and everything's labeled and...
Yeah, semantic segmentation where the sky is pink and the ground is red and Can do stuff like that as well, I think. But yeah, this concept of sparsity, this kind of sparse data concept, I think is something that's serving them quite well. They're an interesting company. They're pivoting maybe a little bit more towards audio these days.
Right.
I know the example we're just talking about is images, but they have FP16 in new generation, which you need for high quality audio. So they're doing audio manipulation. So the demo that I saw quite recently was more like karaoke machine. Let's separate the voice from the background and your pop music.
Segmentation
and then,
I
guess. And then, play around with it, basically have some fun with it.
Okay. So karaoke machines,
but I think there are other applications.
But it's different to noise cancelling.
It's different to noise cancelling because I can do it in real time and then just turn up the voice, turn down the voice, or extract other bits of track that may or may not want to hear. I think karaoke is quite a fun example because it's easy to imagine, but let's see what they come up with on the audio side as well.
Or music to which the masters are lost. Or master tracks.
Yeah, let's like re-engineer it.
Yeah,
remaster it.
Yeah. But we've only got a full recording rather than the individual tracks. Okay, I get that. That makes sense. So many thanks to Tenstorrent for sponsoring this episode. Tenstorrent has multiple generations of hardware. 2 are in production, and there's at least 2 on the roadmap that we know about. They're exploring what the ideal size is for matrix multiply engines. They've got their own RISC-V cores coming out. They're expanding into chiplets, high performance. I've interviewed Jim Keller a couple of times on this channel. You should definitely check those videos out, explaining how Tenstorrent isn't just an AI hardware company. They're a design company. You can expect AI hardware, chiplets, all sorts of stuff to come out of them over the next few years. Keep track on this channel to find out more and click the links in the video description. Also, if you're interested in a job, because they're hiring. So next in the episode was Tenstorrent with their Wormhole processor. So Tenstorrent is a semi-poster child in the industry because Jim Keller's there and everybody knows who Jim Keller is. I actually had dinner with a new employee at Tenstorrent at the weekend, a guy I've known that's been to a few different companies, and he was like, we need to promote that Tenstorrent is more than just Jim.
Okay.
Which is fair enough. I mean, Tenstorrent, I've interviewed Jim, I've interviewed Labisha, who's the CEO, he's ex-AMD, and we all know where Jim's been, AMD, Intel, Tesla, Apple, Broadcom. So their whole thing is let's design a chip that we can put into, that we can sell 1,000 of to a customer. That means we will get customers who want 10,000 to start being interested. Then when we sell systems of 10,000, we can sell to 100,000. So of 100,000, we get to 1 million, and that's when we play with hyperscalers. Talking about Graphcore earlier, their main target has always been the hyperscalers.
Yeah.
So it's basically you have to baby steps. You can't just jump in at the dive end.
Yeah.
And that's kind of what Tenstorrent wants to do here. That Wormhole is their 3rd, 4th generation chip. This is the one that has massive networking
Yeah.
So one of the big things with scaling AI chips, NVIDIA has this especially, is if your problem is too big for the chip, you have to break it up and essentially chunk it in a way that when you do have the cross communication, like an all reduce, which is a synchronous operation, that you're not memory bandwidth starved, and there's additional things you have to put into the software to support that. With Tenstorrent, one core looks like one chip, looks like one supercomputer. Because the way you talk to any other core is essentially over an Ethernet interface, each one of these chips has 1600 gigabit Ethernet interfaces, which then connects to as many other chips as you need, either high bandwidth modes, low bandwidth modes. And I remember speaking to Jim and I said, look, somebody buys a multi-rack system of these. What's the cost of the cables compared to the system? And he went, about half.
Really?
Yeah.
Oh, good grief. Okay.
But this is the whole point. If you're scaling with individual chips and you're not doing big things like wafer scale, you need to have, or something like Tesla Dojo, which is all sort of on-chip SerDes, you have to have this big scalable solution. Now, Ethernet's obvious because everybody knows how to do Ethernet. Sure. You can just buy the IP. One of the interesting things that they're also doing on Wormhole with relation to AI is approaching transformer networks.
Yeah.
So transformer networks, it's basically, to use the same phrase, a poster child for AI right now.
It's like this is trendy in AI right now.
Yeah.
But the thing about transformers is they're very, very, very big, or they can get very, very big, right?
But also, sometimes you're required to do extra in-between layer processing.
Sure.
So it's not just simple AI standard operations. So if you're doing that on a big system like GPU, you do your layers in your network, and then you have to move the relevant data back to the CPU.
Yeah.
Do the extra compute on the CPU, then redistribute it out to your network. Jim was actually at a TSMC event earlier this year. If you're watching 2023, then it's late last year, where they were showing off their homegrown RISC-V core called Ascalon, which looks like a very high performance 8-wide core, but specifically built for those sorts of workloads. So whether Jim designed it or he just managed the team who designed it, it's interesting where Tenstorrent is going with this. Their whole thing is scalability.
Yes, which is crucial.
And I would argue that's perhaps one thing NVIDIA has trouble with, Amdahl's law, with these things.
I don't think they would say that.
Well, no.
Some of the biggest AI installations in the world use NVIDIA chips.
I know, but you're running multiple networks at once and you're subdividing your time. Are you actually running, one massive network on it?
It's like partitioning bits of network across multiple chips and stuff is still very, very hard.
Yeah.
It's still a bespoke process that a person somehow has to come up with how to do this for sure. But in terms of system level, I think they have it figured out. It's more like workload. How do we partition the workload?
Whereas the idea with Tenstorrent is, you've already got your TensorFlow, PyTorch, whatever. And because a core looks like a chip, looks like a whole system, then you only need to compile it once.
No need to build a wafer scale chip.
Depends. Yeah. So of course there are some limits on memory bandwidth, and that you get.
Okay.
So this is why they're still using Ethernet. They have spoken about future generations of chips already. Dylan from Semi Analysis has an article on that.
Okay.
I still need to look deeper into it. But Tenstorrent is hiring as well. They're still VC funded, but yes, they're hiring. They're one of the top VC funded companies now in AI. In the top 10 that at least I track, the ones I track, the ones that don't tell me how much. Right. So I'm looking forward to seeing it. And
me too. Looking forward to seeing what they can do.
Seeing how it tastes.
Absolutely.
So Syntiant.
Sick. Okay. One end of the scale, like right to the other end of the scale.
Oh yeah.
So Syntiant, again, have been around for a little while, I think 2019 or so. And they were one of the first to come out with an AI accelerated chip back when everybody was still like, what is this? Like, what is this going to be? But the thing about Syntiant is it's ultra low power. It's designed literally for keyword spotting, like, okay, Google, and then wake up something else in the system to respond to that. So
when you're saying ultra low power, we're talking not even milliwatts, microwatts.
Basically, yeah, like right down at that end of the scale. Certainly want to be sub-milliwatt for always on.
Yeah.
If it's always listening, right? There are other parts of the system, microphone and stuff, that uses power.
Yeah.
But for the inference, microwatts. So they have a second generation core now, which so they've always been known for keyword spotting. Second generation core, they can do some image processing as well.
Yep.
So visual wake words, that kind of thing, person detection, that kind of thing. But still, again, very, very low power. They're already in consumer electronics, laptops, that kind of thing.
Mm-hmm.
But yeah, it's definitely for the always on, ultra low power end of the market.
It always amazes me that if something's that like ultra low power, surely some of the big companies can already do this, right? Why has Syntiant managed to find a foot into the market?
Why is there a niche here for a startup that I guess ultra low power design is very, very difficult, right? We're kind of talking about power consumption. The ones we're just talking about hundreds of watts, right?
Yeah.
When you get down to the very, very low end, it's harder than you think
right.
to do ultra low power design.
Well,
I can't overstate that, right?
Well, yeah. So if a chip like that, say in my laptop, and it's using quote unquote microwatts, but at idle it's running at 3, or maybe in sleep it's running at tens of milliwatts.
Yeah, but how many more different little chips doing different little functions are in the laptop, right? Every little helps.
That's fair. But maybe there needs to be one chip that does everything. Oh no, wait, that's a CPU.
Oh, hang on.
That's high power. Yeah, I get. I mean, smartwatch is the obvious one. It's
earbuds, like hearables.
Yeah.
Let's put keywords in on voice commands. Syntiant could certainly do that in your earbuds.
Yeah. It's as people who still have smartwatches that they have to charge every day. I have to charge this one once every 2 weeks.
Yeah, likewise. Right. I don't charge very often.
But it doesn't have a wake word, I guess.
No, do I need that though?
No.
Do I really need that?
Yeah. It's some of these chips are also just being developed to enable new use cases, perhaps use cases that we're not day to day yet.
Absolutely, yeah, absolutely.
I mean,
I think voice control, voice commands is going to come to pretty much everything sooner rather than later. So yeah, I think you're going to start seeing voice controlled gadgets around your house very, very soon. Do
you have any voice control assistants at home?
So I have Alexa. Yeah,
right.
I use that version, which is pretty good.
It's I had one for a few years, but when I moved like 3 years ago, it didn't get turned on after we moved.
Right.
So now we do not.
I like it for some things. I use it when I'm cooking.
Yes.
When I am up to my elbows in goodness knows what, right? Then I need voice control. But side effect is now my 5-year-old can turn on the TV when he is not able to use the remote yet. So there are pros and cons, right? Of having voice control.
Yeah. It's almost to the point where you need person detection on top.
You need voice ID and then voice, so only I can turn on the TV. That would be useful.
Or your watch or something, it detects how far it is away and whether that's you. Yeah. I mean, going into the kitchen in the morning, make a cup of coffee, ask it about the weather, the news, play some music. Yeah, that's what I used to use it for. I
mean, I use it as a kitchen timer. Convert between ounces and grams, cooking related tasks, or, connect to my grocery shopping. I've run out of whatever while I'm cooking. Let's use it for that as well, right? So
it's fair enough. So last chip we spoke about on the show is Intel's. They've now called it GPU Max.
Okay.
We used to call it Ponte Vecchio.
Okay.
So we're talking about, again, going from one end of the scale
right back to the other end.
This is literally the end, because this is the big 47 tile monster.
I mean, it's a beast. Like, how many chiplets can we put in one package? It's crazy.
So for the longest time, I've been saying, look, everything when you design a chip has a yield related to it. So if you're putting a chip on a package and your yield is 99%, you lose 1% for losses, and you have to amortize that in the costs. So if you put 2 chips on a package, you have a yield loss of 1% times 1% for those 2 chips.
Yeah.
Now, if you make that out to 47 chips, your overall yield, if you have a 1% loss chip on chip, your overall yield is 64%. So imagine designing such a massive chip.
And you yield 64% overall.
And your packaging yield is 64%. Not even your production yield. I put that to Raja Koduri at Intel. And he said, your math is correct, but we don't do it that way.
Right.
So because you've got this it's kind of like base die, and then you've got compute die on top, and then you've got what they're calling Rambo tiles for the random access cache. That's where the rando comes from. Then what they're doing is they're taking known good die, putting some of it together, and then they're validating that before they package more together.
Yes.
So my whole 1% to the power 47 means when you're packaging them all together, assuming they're all known good die without any intermediate testing.
Yes.
So with that, you can actually get the packaging yield effectively to go up, but that assumes that you have working known good die all the time.
Yep.
So
not all are going to be, not all going to pass that test to start with, right?
Yeah. So this new chip, it's now called the GPU Max series. You're going to have 3 versions. You're going to have the PCIe card at 300 watts. That's going to have 48 gigs of HBM2E. Then you've got 2 OAM modules. This is what does OAM stand for again?
Original Equipment Manufacturer.
No, OAM. That's the Open Compute Accelerator Module. So it's the whole, Facebook did this whole standard thing with OCP Accelerator
Compute
Module.
Project.
Yeah, there we go. Yeah. And so you can get that in essentially 2 form factors, a single one or a 4 one. And the 2 models come in at 450 watts or 600 watts, 96 gigs of HBM2E, or the full 128 gigs of HBM2E.
Yeah.
And then you got 4 of those on a board. That's 2400 watts. Each chip can go up to 52 teraflops of compute. I need to double check that. It's in my notes if that's FP64. But the whole thing is, this is not only a HPC chip, it's going to be an Aurora, which is late. We can talk about that. But it's also going to be used as an AI chip and supports AI training and inference. Having this massive amounts of cache and HBM memory. I mean, the slides that we see are always talking about the bandwidth going between the different cache layers, which is important when you're speaking about big models.
Absolutely. It's all about the amount of data coming out, feeding it, basically.
Yeah.
So,
but the biggest installation for this is Argonne's Aurora supercomputer, which was meant to have shipped beginning of 2021 or 2018, but with a different product. This is it's late, and Raja Koduri, is obviously heading up that team, that project, or the whole division. He's really excited for it. I think everybody's really excited to see it because they've been kind of showing it off.
I'm excited to see 47 chiplets in a package and make that work.
Have you not seen one in person yet?
Soon, Sunday.
We have to get you to Intel Vision next time around, because
maybe next year
definitely have one. But yeah, they've been showing off either the dummies or the failed ones. Again, you have that many chips. We're getting to a point, right, where supercomputers are so big that you're always the average mean time between failures is like minutes. So how do you develop a software stack and a solution that copes with that failure rate?
Yeah,
I mean, the system is still up. We now have systems where if something goes down, it doesn't take anything else out with it. You can just you can live hot swap, a 600 watt GPU. Well, I mean, not me personally. You take
one
system.
One could remove
one
this.
could do it.
Yeah,
but it maybe it's getting to that point with chiplets. I mean, we were talking about in the last episode with NVIDIA where you got 6 HBMs, but only 5 are active.
Absolutely.
So
there's a redundancy.
Yeah.
Level of redundancy.
That's the word I was looking for, redundancy. We already do it in chip design, right?
That's true. Yes, we do.
To mitigate for yield and defects and stuff like that. So
to switch off some cores.
Yeah.
If it doesn't work.
Or and then maybe sell ones that all work at a very high premium.
Exactly.
And that's when you get the best. So yeah, they renamed it. They gave it an official productization name because you can't trademark Ponte Vecchio.
I'm still going to call it Ponte Vecchio.
Everybody's going to call it.
We're going to call it Ponte Vecchio.
I mean, so the whole reason why companies choose place names for their code names is because they can't be trademarked. And the issue is if you're a company and you choose something else, say you call the internal chip name Wolverine, then Marvel's going to come after you if that's used in a commercial setting. Very fine for internal.
Yeah, but if it gets out, like
these code
people
names
start to call it that.
I mean, I've been calling this chip Ponte Vecchio because that's what they've been calling it. But now it's Max GPU. I also have Max CPU, which is Sapphire Rapids with HBM. We'll cover that in another episode. But yeah, when people will get this Max GPU after Aurora's been installed.
Yep.
So, and then after that, you've got other tier 0, tier 1 customers. I'm thinking end of 23.
I think that's a reasonable estimate.
Yeah. But they also spoke about next generation Rialto Bridge.
Okay.
Which is, again, another bridge. Ponte Vecchio is a bridge. Rialto Bridge is a bridge.
Yeah.
And that's going to be what it looks like, just an architectural update. But the design is the same, and it's meant to be, I believe it's meant to be sort of, package compatible, socket compatible. And then after that, we get Falcon Shores, which is, CPU plus GPU plus everything else in a package, which again, we'll come to in a future episode. But yeah. How have you felt about Ponte Vecchio?
Curious. Yeah, it's so different. So many chiplets and so different. I'm interested to see if they can pull it off, basically.
Yeah.
Like we're saying, it's something so completely new. I wouldn't say I'm skeptical. I'm just curious.
Yeah. As long as the cost stays 5 figures, I worry that it's 6. I mean, when's the last time you saw a quote-unquote regular-sized chip package sell for $100K?
Yeah, I mean, we haven't really talked about cost much at all so far, but it obviously is very important.
So when you're in a supercomputer like Aurora, TCO is not the primary thought. You have a budget and...
Well, at such scale, the cost of the chips is going to be big part of it.
You're factoring more the total cost of ownership over 3, 5, 10 years.
Yeah.
And then obviously this is also a government grant, right? It's not a commercial deployment.
Yeah, where they're balancing with how much money can we make from this installation.
Yeah.
It's a little different.
So Intel hasn't spoken about that much, but that's because they just haven't got any to share in that same way. So
we'll have to wait and see.
Yeah. So that's pretty much it for the end of the second episode of this, sort of chill down room chat. We do have some more coming. Episode 3 is actually quite a doozy.
It's going to be a good one.
It's going to be a good one. Stay tuned for some hot takes.
Okay. Yeah.
So, if you're watching this as it's coming out, the next episode will be next week. If you're just watching it casually, then check down below and see if we come up on your must-view next list.
See you next time.
Thanks, Sally.
Bye.